Today's topic is electrostatic potential and capacitance. In first year we studied about gravitational potential and also about elastic potential energy. So work done against gravitational force is stored as gravitational potential energy. Similarly, work done by the elastic force is stored as elastic potential energy. Similarly, whenever work is done in an electric field, then that work done is stored as electrostatic potential energy. Let us consider, so first of all we will discuss about the potential energy. So electrostatic potential energy. So let there be a positive charge, say some Q. Now at some point P, and here a charge plus Q is brought, say some other point, say some R, like this. So let us suppose this is delta R. Therefore, since it is experiencing a repulsive electric force, that positive charge, to bring the charge from some point to this point towards this charge, then work, you have to apply some external force equal to this but opposite in direction. Therefore, this work done can be written as F external bar into this delta R bar. But you know this external force is opposite to this electric force. So this electric force can be written as something minus F electric force dot, say, delta R bar. Now this is for a small displacement. So if you bring from a point to another point a large distance, because the force is not constant at every point, it varies inversely with the square of the distance. Therefore, generally we write the total work done in moving the charge Q from some point to another point. The work is given by minus integral of, so Fe bar dot dr bar. So that delta R bar can be taken as dr bar. So from a point R to this point P. So this work is the potential energy difference between P and R. See, when we bring the charge to this point also we have to do some work. And so the difference of these potential energies at R and P is given by this work done. Therefore, we can also write it like this: W is equal to potential energy at P minus potential energy at R. So, suppose if you are bringing this charge from a point at infinite distance where there is no electric field, so at that point you may take the potential energy of the charge to be 0. In such case, so that if you say that R is at infinity, then this work done is from infinity to P. There is electrical force dr bar. So from infinity to P, when you bring the charge Q, so whatever work done will be the potential at that point. So in this way, potential energy of a charge at a point in an electric field is defined as work done in bringing the charge from infinity to the point under consideration without acceleration. The meaning of without acceleration means if there is the charge is accelerated, means some extra force is to be applied. So therefore, you have to apply equal force to that of electrical force externally, but in opposite direction. So that's why you got negative sign, and hence this is the equation for the potential energy of a charge at a point in an electric field. Then we will discuss about electric potential. So we discussed about electrical potential energy of a charge. Now we will discuss about the electrostatic potential. Electrostatic potential. Suppose the charge you are bringing, that is this test charge, is of unit value. Then how do you write this is, that is work done per unit charge. So this you write like this, from infinity to P. So you got dot dr1. This is the total work done. So per unit charge, how much work you did. So that is defined as electrostatic potential. So the potential energy per unit charge is defined as electrostatic potential. Okay. Now we will derive, using this formula, we will derive the equation for the electrostatic potential due to a point charge. So electrostatic potential due to a point charge. So let us consider a charge plus Q. Now at a distance r from this you are bringing a unit charge plus 1 charge along radial direction. One more important point regarding the potential energy is that, so in the explanation I might have shown you, the charge is brought along a straight line, but the potential energy doesn't depend upon the path taken in bringing the charge. You may bring the charge in any way or along any path, but it is independent of path. This is one characteristic of conservative forces. We studied in gravitation also. That is, all conservative forces, the work done will be path independent. The work done by conservative forces is path independent. Therefore, they depend only on the initial point and the final point, only on the position. So it doesn't depend how that position is attained. So similarly, in electrostatics also, whether you bring a charge in a roundabout manner or along a radial direction, the work done is same. Therefore, the potential energy of a charge in an electric field is path independent, but for convenience we take a radial path. So let us assume that this test charge is brought from somewhere infinity, to this point P. Now here let us suppose this point, we assume that is say some at a distance of say some r dash. So let us say this point is say some r dash. We say some r at a distance r dash, that point be some capital. So for a small displacement, let us suppose delta r dash. So we know, let us suppose at this position, the electrostatic force due to this charge is given by 1 by 4 pi epsilon naught according to our Coulomb's law. So capital Q, and anyhow you multiply it with 1 because you are bringing the unit test charge. Therefore here you kept that unit test charge, you have to imagine. So by r dash square, and let us take this r dash cap as the unit vector in the direction of the electric field or electric force, or sorry, along the radial direction, let that be the unit vector. Then, so I want to calculate the work done. So for calculating work done, what I have to do? So you are bringing against the electric force. So therefore, work done is given by minus integral of this 1 by 4 pi epsilon naught q by r dash square. So you brought it by a small displacement delta r. So let us put that delta r dash, or you can put dr dash. So here the vector notation is not necessary again, because already you have taken the negative sign. So because the displacement vector, force vector are opposite each other, so automatically you get the negative sign, and you brought it from infinity to the same point P. So this is for small displacement, and for the entire displacement from infinity to a position at a distance r bar from this q, total work done is given by this. So that leads to this minus 1 by 4 pi epsilon naught here, okay, q, and you will be getting minus 1 by r, and the limits are from infinity to r. So let us suppose this is r dash, because you have taken the r dash square. So minus 1 by r dash between the limits infinity to r. So if you substitute the limits for r dash, you substitute infinity, that is 0, and the minus of next plus, therefore you can write like this 1 by 4 pi epsilon naught q by r. So this is the potential at a point P due to an electric field of the charge q. And you must remember that the position of this q, or location of this charge, should not be disturbed by the charge you are bringing, the test charge you are bringing. That's why we take the test charge to be very small. For calculation purpose, we have taken it as q to be plus 1 unit, and we assume that it won't disturb it. Okay, so this is the expression for the electrostatic potential due to a point charge in an electric field. So you have seen that due to a positive charge, the field will be considered as positive field. Work done is positive, or potential will be positive. So if you have a negative charge, the field may be negative field. In such case, the potential will be negative, because the force will be attractive force. Therefore, you will be getting negative sign for the potential. So if work is done on the charge, the potential will be positive. If work is done by the electric force itself, it will be negative. So in that way, we can derive the formula for electrostatic potential due to a point charge. Okay. So if you have a system of charges, so what is the electrostatic potential at a point for a system of charges? Here simply we apply the superposition principle. So that is, we know that algebraic addition, here it is potential is nothing but work, which is a scalar quantity. So therefore, potential due to all the charges at that point, we have to add algebraically. So generally we use the symbol V to represent the potential. So suppose if you have several charges at different positions, say so here say some Q1, here say some Q2, here say some Q3, like this. Due to all this, I want to know the potential at this point. So calculate the potential due to each charge and add them. So it is something like V is equal to V1 plus V2 plus V3 and so on. So to bring a unit test charge from infinity to this point, against this one, against this one, against this one, what is the work done? So that individual works, you have to add them algebraically. So if use the proper signs for a positive charge plus sign, then for negative charge minus, like that you add. So finally what you will be getting? This 1 by 4 pi epsilon naught is common. Then you will write Q1. Suppose this distance is R1, and for the second charge, say R2. For the third charge, say R3, and like that you go on putting proper signs. So for a system of charges, the electric potential at a point can be calculated using superposition principle. Okay. Now we will go for a dipole. In the case of an electric dipole, how we are going to find out the electrostatic potential at a point? So you will see something different in this case. You know, electric dipole has two equal and opposite charges. So let us say this is minus q and say this is plus q. And let us suppose the separation between these two charges, we say some 2a. So that is the separation between this, and this is the midpoint. Now, so choose some arbitrary point. Here in the last lesson, we discussed about the electric field strength due to a dipole. There, the electric field strength not only depends on the distance of the point, but also on the angle between the dipole moment direction, that is direction of the dipole and the position vector. So that means in the case of a dipole, the electric field strength not only depends upon the distance of the point from the center, but also on the angle between the dipole axis and the position vector. Similarly, here also we are going to show that it depends on the direction of the point. So let us suppose this is the center of the dipole, from which here we take this as say some r. And from this charge, let us say this point P is at say some r1 bar, and this minus q is say at a distance r2 bar. Now let us assume this is some angle theta. So you know this is A, this is A, and you know the direction of the dipole is from minus charge to the plus charge. Now the potential to each charge you can calculate and use the superposition principle. So then what will be that? That is resultant potential 1 by 4 pi epsilon naught. Here q by this distance r1 minus q by say r. So our usual formula, what we got in the derivation, so the same formula used. So due to positive charge, positive potential, due to negative charge, negative potential, as summed up. Of course, you can take that q also common and can be written as like this: 1 by r1 minus 1 by r2. Now, from the geometry of the figure, you can substitute for r1 and r2 in terms of r. So, using that vector concept, we can write like this: this r1 square is equal to r square plus a square minus 2ar cos theta, and similarly r2 square is r square plus a square plus 2ar cos theta. So from the figure, using the vector concept, we can write like this. Then from this you can simplify it further. That is here I will write like this: r1 square can be written as So I will take this r square common. 1 minus 2a r cos theta here by r square plus a square by r square. So 1 r gets cancelled here, and therefore I can write directly. And one assumption, we can drop one term here. See this one. So let us assume that the distance of the point you have chosen is far greater than the separation between the dipole charges. So that is A. So if R is far greater than A, you can neglect this A square by R square. So you can neglect the A square by R square, and then what will be this? 1 by R1 square. So I am taking this 1 by R1 square is equal to 1 by R square, and in the brackets you will have 1 minus 2a cos theta by R to the power of minus inverse. Now if I take the square root, so I can take these two outside and I can write like this. So by using binomial theorem and writing the expansion and limiting to the first order, then higher powers, if you neglect, this can approximately is written as 1 by R into 1 plus 2a cos theta by 2R. 2 gets cancelled here. So therefore it is 1 by R 1 plus a cos theta by R. Similarly 1 by R2, so from this equation can similarly be written as 1 by R into 1 minus a cos theta by R, like this. So from these two equations, let us substitute here in this equation for 1 by R1 and for 1 by R2. So then what will be that? So V is equal to Q by 4 pi epsilon naught. See here 1 by R1 minus 1 by R2 means this one gets cancelled. So what remains is here a cos theta by R square, and here minus of minus plus a cos theta by R square, because this one gets cancelled. What remains is a cos theta by R square. Here also minus a cos theta by R square, but that minus of minus will be plus. Therefore, what you are going to get is 2 times a cos theta by R square. This is what you get. So substituting for 1 by R1 and 1 by R2 in this equation, the formula will become like this. Here I will rewrite it like this: 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, and 2a into q by R square into cos theta. See here, you see this one, 2aq is nothing but dipole moment. P is equal to the charge multiplied with the distance between the charges. So that gives the dipole moment. So therefore, this is the dipole moment. So let us represent it as P. And if you take say some P cap as the unit vector, or say some R cap as the unit vector in the direction of R bar, this formula can be written as a dot product. Okay, so I will write it here. Therefore, V can be written as 1 by 4 pi epsilon naught. This is dipole moment dot R cap, unit vector in the direction of position vector, by what is there? R square. Now, this is the formula. Here, you see that the potential to a dipole depends on the direction of the point, that is angle between the dipole axis and the position vector. So, here it is varying inversely with the square of the distance, whereas in the case of a point charge, potential varies only inversely with the distance. Here it has inverse square dependence of distance. So, that is this. Now, one more point we can discuss here is, suppose if you rotate this position vector, keeping the angle constant, you can imagine something like a cone is described, is it not? So, at every point similar to the point P, at every position similar to this point P, the potential will be same. So, you can think of such points having same potential. So the positions are different, but the angle, if you keep this angle common, then you can say that they are at the same distance from the center, hence and the direction is also same. Therefore, you will be getting the same potential for every point on the circle described by the cone, with R as the side of the cone. Okay. Now, that is about the L. And one more point. So, if you imagine this point to lie exactly on the axis of the dipole, if the point P lies exactly on the dipole axis, theta will be 0 or pi. So, theta is 0 or pi means the potential will be maximum. So, because cos 0 or cos pi gives plus or minus 1, therefore the potential will be maximum along the axis of the dipole. So, for theta is equal to 0 degrees or pi radians, then the dipole potential is maximum at every point. Suppose you have theta is equal to 90 degrees, that is pi by 2. Then you will have equatorial plane. So at every point in the equatorial plane, the potential will be 0. The reason is, you know, cos 90 degrees is 0. Therefore, at every point on the equatorial line or equatorial plane, the potential due to the dipole will be 0. Okay. So that is about the electrostatic potential due to a dipole at a point. Okay.